Okay. Alright. So it's 9:20. 2 weeks clinic, right? Future CDE, quality, Fahim, myself, H. Okay, sir. Right, on schedule. Fine.
So good afternoon, everyone. I'm Fahim, and this is my student lecture for the day. We are finally in the last chapter of the textbook, which is chapter 12, talking about future CDE technologies. As usual, this is the reference book, and I will be covering 12.1, which is the objectives, and 12.2 until top-down design, and the rest will be covered by Professor. So until now, we know that feature-based modeling had not been developed for all types of design and manufacturing tasks. And in this lecture, we will look at some research and directions for product modeling that go beyond feature-based modeling. Feature-based methods need to be extended for the early stages of design, where the designer is more concerned with function and overall structure than the detailed geometry. So the objective is that, previously we knew that the main goal of product modeling was to communicate the design information of a product to planning and manufacturing. We could say that the features were based on an extensional view of design. What this means is that we observed what the designers do and capture recurring aspects of their work in feature models. However, this leaves out the intentional aspects of the design. Intentional aspects means what the designers really think and do when they design. A fundamental problem of product modeling is to find concepts and tools that will allow us to extend into the intentional realm of design. This is a design process which has differentiable phases, and each phase has its distinct goals. In the early phases of design, decisions concerned with the characteristics and overall function are made. And in the later phases, specifications generated during the early phases are elaborated to ensure that the product fulfills the specifications and can be manufactured quickly. Therefore, design information is gradually growing from vague and fuzzy sketches to very detailed descriptions. Then, the detailed descriptions are transmitted to downstream phases, such as process and assembly planning. So in this figure, you can see the importance of early design. This is a submarine, the production of a submarine. The x-axis shows the time. There is some text, but I think it's too light. So this is the cost, time axis, and the y-axis is the cost axis. And here is the early design stage. And you can see that if the committed cost and changes are high in the early design phase, then the risk and cost later on in the production stage is much lower. However, if the early design is not well done, then later on the accumulated cost can be much higher, and small changes can result in much more increased cost and risk. This second diagram, which is by DARPA's RADIO, which is a Rapid Design Exploration and Optimization Project, shows something similar. It shows that 70% of the total product cost is confirmed at the product development stage, which is the conceptual design stage. And most significant cost saving opportunities are in the early stages of development before the product is mass produced. So as you can see that the life cycle cost determination increases as time goes on, and cost reduction opportunities decrease. I added this figure, which is similar to the submarine. It shows two companies, Company A and Company B, which manufacture. So Company A made many changes in the early design process stage, and they changed the design of the car before it went into production. And company B shows that the company was still making changes after the design had been released for production. Therefore, 35% of the cost of the company B occurred after it was in production. Early design changes require more engineering time and effort, but they do not require changes in hardware and documentation. So a change that would take $1,000 in the early design phase may end up costing $10,000 after it was produced, and maybe even $1 million or more in tooling, sales, and goodwill expenses. This diagram shows how important the early design stage is. Now I would like to talk about the decomposition of the design process. So this is one way of breaking it down. First is a functional design, which focuses on the function of the product. That is, what must the product be good for? What are numerical or quantitative functional requirements on its performance? And what undesired behaviors must be prevented? Second is the conceptual design. This is where a basic engineering structure is provided for delivering the desired and avoiding the undesired functions. In this stage, ideas are generated and evaluated. Embodiment. This is where the result of the conceptual design phase is mapped onto a realizable structure. Then is the detailed design phase. Here, the result of the embodiment design stage is elaborated to a sufficient level of detail, and it is determined by the manufacturing processes. Lastly, we have the engineering analysis stage. Here, the results of the design, detailed design are investigated against functional specifications. Another way of decomposing the design process is if we consider innovative design, which considers products made towards customer needs. So here, first the customer requirements, and the next two steps are similar to that of the design process which I showed earlier. Now I'll talk about preliminary design. The early stage of design, which is functional, conceptual, and embodiment design, are not very well supported by the present product modeling methods. The function, behavior, and structure, FBS, are the key aspects for better coverage of design activities. First, let's talk about the expert system. Problems, human experts. Domain knowledge from the inference mechanism. The between expert systems and algorithmic solutions is that it has separate domain knowledge. And one of the original deficiencies of systems was the handling of geometric information. That is where these two systems came in. One of them is ICAT, which is a knowledge-based system which combines knowledge base and geometric modeling. And the second is Design++, which forms a dynamic link between a knowledge-based system and AutoCAD. Now, this is the top-down design. Design is a high level of abstraction. And ideally, we go from a high level of abstraction stressing the function of assembly to very detailed models of individual components. And going from high level to detailed models, there is transition between. In this image, we can see the transitions from a conceptual sketch of a component connector to a base unit layout, and finally a feature-based component design. So the requirements for modeling facilities to have top-down design is that there should be levels of abstraction. The model should support representing the information on several levels of abstraction, which are abstract structure, overall geometry, and detailed geometry. Also, it should represent design intent, and it should support abstract geometry, which is intermediate design, where there is no commitment to a detailed design solution. So assembly design, an example I will show in the next slide. It is the model by Struss, where components and connections are joined at common terminals, and there is a hierarchic structure. It uses ATMS, which is assumption-based truth maintenance system. What this does, it allows accommodating different parallel designs. The problem with Struss's model is that it cannot geometrically represent component shapes, since it supports diagnostics mainly. And the major disadvantage is its inability to relate changes made in one viewpoint to the changes in another. So this is Struss's assembly model. As you can see, the terminals have substructures, and components and connections are represented through variables. Terminals denote shared variables. And the functions of design are described by equations and constraints. Now we will talk about p-graphs. And p-graphs are part graphs for assembly modeling, which combine multiple viewpoints. They are also hierarchical, with nodes representing objects or sub-assemblies, and edges representing constraints and relationships. The main difference between this and Struss's assembly model is that it is capable of editing and retrieving database, and also propagating changes made in different viewpoints. There are multiple ways of representing the same assembly depending on the type of viewpoint. Here is an example of p-graph structure of a lamp assembly. As you can see, the lamp can be broken down into two nodes, which further can be divided into two each, such as stand, top, electrical system, and support structure. And the top and electrical system nodes can also be divided into many subnodes. And you'll see that many of these nodes are linked with multiple different superset nodes depending on the viewpoint. Next is the Edinburgh Design System, EDS. This allows two different types of modules, which are the concrete module and interface module. Concrete modules contain parameters and variables which are explicitly specified. That is, concrete modules display features. Interface modules specify constraints between parameters and variables, and they show the spatial relationship between features. In this image, you can see the top diagram is a concrete module which shows this gear structure, and in the lower diagram, you can see the spatial relationship between the features of a gearbox. A computer program can be used to derive the relative position of bodies from the modules. Logic-based systems are another type of assembly program, and they use logic-based mechanisms. A lot of times, designers may work with incomplete geometries, and some important details are represented exactly, whereas the rest are vague or unspecified. So logic-based geometries on the basis of incomplete constraint-based descriptions. The system divides constraints into two types: tight constraints, which must be strictly satisfied, and loose constraints, which specify properties that are desirable for manufacturability and product quality, and are used for optimization. So in this diagram, it is showing a sheet metal part, and as you can see, the detailed shape is unimportant except for a few portions such as these two holes and that of the contour. The tight constraints are that the contour must contain pre-specified segments. The holes and cavities must have specific tolerances. The narrowest width must be greater than the ability of the manufacturing machine. And the line segments must either be horizontal, vertical, or mutually diagonal. So contour generation can be solved in two stages. First is the initial contour made from tight constraints, and second, constraints satisfied to the maximum extent possible. So initial contour is generated by two methods. First is the envelope method, which contains all the holes, tight constraints, and required segments, and is created algorithmically. And second is the configuration method, which specifies the rough shape of contour using skeleton. So here in the image, you can see figure A shows the initial skeleton, and figure B shows primitive shapes satisfying the constraints generated around each connection in the skeleton. Part C shows the primitives finally combined into the overall contour. So once that is done, we move on to the contour refinement stage, which satisfies the loose constraints. In here, shape modification rules are used, and you can see 3 examples, such as if the angle between the 2 segments is almost correct, then you make them correct. And if there is a small chamfer at a corner, then just remove it. And lastly, if the lines are almost parallel, then just make them parallel. So these are the shape modification rules which satisfy loose constraints. That is all for my presentation. Any questions? Nope. This is just the initial contour. Contour refinement is shown here.
It is a skeleton. Start from skeleton. It is better to say this A can be a skeleton.
More questions?
I want a little bit more explain about the shell or exposed system. Shell is something like this one. Shell. But I found that shell is Dutch Royal Shell is a very famous company, oil company. So they probably changed seashell. Anyway, shell is the outer skin of shell. So we can expect that this is outer structure. So there is no contents inside shell. Exposed system shell. You can purchase. It is very similar to database management system. Oracle. If you buy an Oracle system for your use, you just buy a shell. Shell means some container and some algorithm together. No data inside. No data inside. Similar to this. Here, exposed system shell is a commercial system. You purchase, there is no expert inside, no knowledge inside. No data inside as Oracle. You should put knowledge inside. Then it works. Same as Oracle. No data inside. You should put big data inside. Then it works. Alright. So, shit. My part. And final chapter and remaining parts. Function-based design, bone graph, collaborative design, design history, configuration design, qualitative reasoning. Those are new ideas for feature-based design. But it is all said long time ago, right? Many of them are developed, but still some of them is going to die out. Function-based. Same as function behavior structure, FBS. I mentioned about this part. So functionality of any machine. Function hierarchy. Functional decomposition. So I want to design a ship or airplane. What is the function of airplane? It is to carry passenger or cargo through the air. That is the top level function. And then you need to decompose functions as a tree. And final node can be parts of the airplane. So function of the fuel or tire, function of the jet engine, function of wing, function of seat, function of cockpit, many, right? So functional decomposition is. So in early creative design stage, designer knows the required functionality. What is the required functionality of the airplane? But at the beginning, you don't know what can be the implementation and appearance at the beginning. Airplane, you know, because there are so many airplanes already. You know, rough idea. But if you want to develop a very new airplane which can fly to the moon, then you cannot imagine the shape. You may combine traditional airplane with Apollo or something. But so the detail is not yet known in the early stage. For the creative new design, creative, not traditional, redesign, right? It's a new design. So this is a function, behavior, structure. So we start from here. And then we need to have a behavior. But these are all interacting each other, right? The structure. What can be the material for tire? It can be plastic, right? It can be other, or steel because the tank is moving based on steel tire, right? So depending on the requirement or environment. And then if you take a tire as a steel tire, then behavior is different. And then function may be met or not met, depending on the situation. So you need to work around this puzzle. Function-based design. So design function should be determined, and then the functional decomposition, and then the end node can be realized by a physical thing. Okay? And then should evaluate the model, the physical entity, the structure, and then the behavior should be evaluated. What and side effect of behavior. And then so structure, behavior, function is interacting each other and evolving into a good design. So there is one example of contactor. It was shown by Fahim's slide earlier, but it has a more detailed view here. SysFund is a software but developed probably by Singapore, Finland, Helsinki. Function and behavior. So function, behavior, structure. The software system, physical element. Physical is a structure. And another view of function-based structure, and there's more, right? There's more. See, what is it? Compress, function, context, goal, behavior, P is what? Anyway, synthesis and analysis and evaluation are coming together. So synthesis is combining integrity. Bond graph is another way. The new idea at the time is use of energy ideas. So of course, so it's a more physics-based. Quantity, flow, energy, force, and then effect, and volt and current, and force and speed. So it is for dynamic system simulation. A car, or robot, or airplane, or ship. So various types of system or part components can be modeled by bond graph ideas. a simplified modeling. So there is a port in bond graph, storage process, dissipation because it's energy ideas, and conversion, energy conversion. So energy and flow energy and conversion energy and then the energy. And there is a kilobvolt loads. It is coming from electrics circuit. There is a common bond graph terms and symbols coming from. So it looks like a machine vibration and damping and also electrical graph, right? So you may use energy and electrical circuit, and also it can be used for the force and momentum system, mechanical too. So now they are applying bond graph to mechanical system of cars, axle, back axle, not front axle. So energy is flowing, and then transformation, interface, flows. Now we go on to the collaborative design system tools. So collaborative design, you should have a collaborative partner, right? Nowadays, as I mentioned in previous slide or lectures, outsourcing is growing, right? I may show you the Rouge factory of Ford company. Okay, Rouge factory of Ford company. And T1 car, do you know T1 car of Ford? 100 years ago. It's a start of mass production using conveyor belt 100 years ago. At that time, the Rouge factory, inside the factory, they produce most of the parts of the car, including glass, tire, and also steel plates too. They have a steel mill inside the factory of Ford company. Now, the Ford company, 100 years after now, they have only one single assembly line there. All the parts are coming from outside. So one conveyor belt, maybe long, but it is rotating conveyor belt. You can go to that factory now. I have been to their Rouge factory in Detroit, Ford. But the old factory was very big. Now they converted into Ford Museum. So I can pay money for the museum ticket and look around the Ford Museum. And the final cost is a small portion of assembly plant. They're still producing car there. Only a small portion. Final assembly. But the others are all outsourcing. All parts out. Only final assembly. So then you need to have a collaboration. Probably 100 years ago, the collaboration was inside the factory. Many people working together in one single site. But now it's far away. Maybe parts coming from Pakistan? No? France? So it's a world production. So you need to have a standard, you need to have a modular, you need to have quality control. See, quality control is more important than before, right? If you the transmission is coming from France to Detroit, it takes probably 1 month. They do not use airplane, they may use ships, right? And then after 1 month, they found that transmission is not working. What happened, right? Quality control is more important than before, 100 years ago. Reuse, compatibility, and change propagation. Because every time, every design, there is a changes, right? Change propagation is go well to the France too, right? And then adapt it there and quality control and make sure that the arrived final product is working together. design history. Engineering design history. Step by step. The sequence, the event means there is a timeline. And state, every state is a time, along the timeline there is a, each state has a, because of the event, state is changing. So time sequence is important. We play the use of this history. Right? If you have a good, we call it a white book of, say, good design of Apollo or airplane 747, white book, we call it white book. After finishing a project, you should have a good documentation. Like as your term project report. I want to use that term project report for the next semester to give them to new students. Then they see that and start again, but better than you, right? Because they have more information there. So it is a replay and the use of portion of the design history of software case. Explain and analyze. And learning, case-based reasoning. Means many design cases. Or law sheet in a law case. They have 100 years of law cases, history of sentences. So the lawyers are looking for the cases. So now they use computer, big data survey, to try to find out the same similar cases or law cases. And backtracking because it is history, so because this is a problem because there are so many cases in 100 years ago, so it is a burden to designers if it is not structured. So it's a query, deep learning, the searching, it is important, and also interpretation. Object-oriented database management system is also good for structured organization of cases because it's not a simple numbers. So product data, design steps, and relationship of design steps to product data. It looks like this in the design history data. Right. So history-based modeling. We are working on this one because it's parametric. They know the history of chess game, right? Chess game I showed you before. Configuration design, configuration management is now important because of the BOM, bill of material, supply chain management. The bill of material, same car as say Ford's car, let's say truck T120 truck. Ford is very famous now in the United States. It's a big truck, pickup truck, probably the wheels not. But for example, assembly is the transmission is coming from France. Anyway, if that same car, say, let go on to a Korean case. Sonata car is a very famous car in Hyundai Motor, right? Best-selling car of Hyundai for the one type. They produce Sonata in China, United States, and Czech, Turkey, India, China included already. Right. Then the BOM is different for each plant. There are plant. Hyundai Motors plant all around the world, probably more than 10 plants all around. And among them, probably 6 or 7 are producing Sonata because that's the best selling car. But each same Sonata, but the components are different because two reasons. One is suppliers. They try to use local suppliers as much as possible if quality is good, right? The other one is localization of specification. In Saudi Arabia, the weather is very hot, so you need to have a high capacity air conditioner than Korea. So it is localization also gives you different specification for components. So that BOM, the same Sonata car, same design, BOM is different for each plant. Right? So we call this as a configuration. Assembly tree, almost the same, but in leaf node level and some branch level, there is a difference. How can you manage these configurations, different configurations? Supply chain. You should purchase some components from the local company and also global company from France, also too, right? So it's a complicated thing. Design also, you know about this configuration, different BOMs. How can you process and automate? Right, and then configuration modeling tools. So configurator is in the middle, standard parts, and users, and there is a rules of combination. There's a permissible or allowable combination between Lego blocks. Check validity between configuration, and also design changes, and components. And challenge to configuration models can be maintenance or configuration. Nuclear power plant. BOM includes millions of parts, but it stays 50 years of operation. Then probably after 30 years, the configuration is probably 30% can be changed, replaced. And also new devices are added to that plant. So there is long-term maintenance. State of the art and current work, XCON is a software system, but it was not easy. But there was also internet CAD system like ITEL, design class, and it's also long, more than 10 years old. Now all systems have changed. We should have a new survey on this. And this is a design method and configuration. Knowledge and then case-based and also special. So these are structure for that kind of design method. Well, one of them is configuration design. Finally, we go on to qualitative reasoning, QR. This is more related with AI. Reasoning with the knowledge rather than data. Knowledge, common sense. It's a kind of knowledge, but it's a general knowledge, right? It's not specific knowledge. So, expert system is they are using very specific knowledge coming from expert. I am an expert in medical expert. A long treatment something, right? I have a very specific knowledge on this long treatment. So based on my special knowledge, using computerization of special knowledge, the purpose of expert system is to replace special knowledge. But common sense knowledge is different. General rules. Everybody knows about this, common sense knowledge. So there is two different ways of approaching AI. One is using very specialized knowledge, one is using common sense knowledge. So they try to solve any problem because using common sense. This one is trying to solve only specific problem, long problem. Two camps study. Quantitative models, qualitative models. There should be key parameters, real numbers, also to conceptual. Right. So what is qualitative? He's saying more than one ton mass is approaching your head by speed of 44. It's not helping to him. It's not. Look out! It's more good. So what is this? Not mathematics. It looks like qualitative, not quantitative. You see, quantitative. Simple explanation. Right. So product modeling, feature technology, solid modeling. We see many of them. And then, more slide. Is I put this. I think I showed you before this one. This is coming from a talk of a high-level senior engineer from NASA. I have attended this one many years ago. But anyway, he is saying new technology at the time was internet, VR, and AI. Still working. Right? We are working more divide more detailed formulas like e-engineering, collective commerce, PLM, and AI, and deep learning. So this is coming from Katia, I guess. We started from 2D, 3D, and digital mock-up, and virtual design manufacturing, virtual manufacturing, and now I don't know. It's post industrial, smart manufacturing something. And VR start from research, academic, and then apply to real industry problems, and that gives you back to. All right. Test Jones. And then we go on to discussions.
Okay, good afternoon, everyone. I will be leading today's discussion session. And here are the topics that I will be covering today. So the first one will be about haptic technology. If you're not familiar with it, it is haptics relate to our sense of touch, and haptic technology is the use of digital information or signal to stimulate our sense of touch. Then for the second topic will be about the automation during the design process. I will first show you this video relating to haptics. So this is from an institute in Denmark, I think. Oh, is there no sound? Yes. So for this case, they use electrical signals to stimulate the muscles and create feedback. And based on what he sees in the virtual goggles.
Signal is coming from the graphic, or it's coming from the body?
It's from the gloves. The gloves induce electrical shock to stimulate the muscles. I'm using my speakers right now because it's maximum. So ideally, when you want to carry this virtual cube, you want to feel the force in your hand, equivalent to the weight defined by the cube. Then for the next video, this is by Microsoft Research. Instead of using
numerous haptic controllers to render objects in virtual reality.
instead of using
However,
electrical shock, it uses
use of both hands, and
hardware to create the force feedback.
We present haptic links, electromechanical connections which attach to standard VR controllers to enable intercontroller force feedback through variable stiffness actuation. In this clip, the user quickly switches between dual pistols and a rifle held in both hands. Attached to their VR controllers is a haptic link. The haptic link allows for full 6-degree of freedom motion while shooting the pistols. However, when using the rifle, the haptic link joining the controllers becomes rigidly locked, allowing the user to handle and aim the gun like a real two-handed weapon. We can also render variable stiffness along a continuous range. Here, as we pull back the drawstring of a virtual bow, the hinge between these controllers becomes increasingly stiff with distance, then relaxes upon firing. To appropriately position controllers to render a new object, we introduce an input method that we call summoning. That is, the user performs a gesture which moves their controllers into the proper position, enabling our system to haptically render the object through stiffening. Here, the user can summon either a car or a motorcycle by holding their hands in the shape of a steering wheel or handlebars. We designed 3 haptic links capable of rendering different types of intercontroller feedback. Each haptic link attaches to an existing unmodified VR controller. The first link is a highly articulated ball and socket chain with a cable threaded along its length. Linear actuators mounted to the controllers pull this cable tight, pressing each ball into the neighboring socket and globally stiffening the chain in its current configuration. Our second haptic link uses a hinge composed of several interleaved layers. By compressing these layers, we increase the friction between them and create a braking force. While the hinge controls the distance between the controllers, a ball joint beneath each controller enables rotation, which is locked using an actuated set screw. Our third haptic link uses the same ball joints, but has a directionally selective brake on its hinge. Small servos disengage the pawls of 2 opposing ratchets, allowing for inward motion, outward motion, both or none. This design enables us to render walls and surfaces, such as in this interaction, where inward motion is halted as the user grasps a virtual object with both hands. These last 2 designs allow us to constrain particular degrees of freedom while leaving others free, such as in this example, where the controllers can move together and apart in a locked orientation to render a trombone interaction. We envision a number of extensions for these devices, such as manually grounding one controller on the body or on another surface, to enable grounded force feedback interactions on the other controller. Our paper describes the design and implementation of our haptic links, as well as interaction techniques and scenarios.
So with these 2 videos in mind, I want to say that ideally for haptic technology, you want a bidirectional communication between you and the computer. So whatever you do in the real life, you have to actually see the effect in the virtual screen, and whatever you do in the virtual screen have to be felt in the real world. So with this in mind, the way to define the features or the geometric models or the solid models in the virtual world has to conform to how you want the objects to behave and how they can create the force feedback for you. So I want to say, what kind of applications does this technology have, and what are the pros and cons, to start with the discussion? Or any other general opinion?
Yeah, training workers.
Yeah, training workers is one. So maybe I will give several examples to start. So first one is a surgical simulation. Before you actually perform the surgery, you can perform them on a 3D model and to simulate the surgery. And the second one is obviously for entertainment and virtual reality. And then you can also have 3D sculpting or painting. And for the industries, maybe you can you can create an ergonomic design. If you want to test for the ergonomics of your design, you can do it first in the digital data instead of creating the prototype. So anything else? Anyone wants to add?
One thing could be the exercise of muscles.
Yes.
In the game, you can define your forces to do that.
Okay, for the exercise of muscles is actually a good idea because then you can save space in your room instead of using exercise machines. You can just use the two remotes. Anything else?
Might be a good alternative to flight simulators, maybe.
Simulators
Can mimic the environment, I guess.
I guess the current flight simulator machines, I guess today could be quite expensive. Maybe it's one. I could add any more suggestions here, but if you guys have anything else.
Simulate training, training can detect whether the constraint is your training.
Yeah, that's one way. So detecting constraints, besides assembly training, maybe, for example, you can have, it can help with customer repairs. If you buy a product, maybe a car, and then the company provides you with a 3D model of the car, and then you can just try to see what's wrong using this first before actually fixing your car, something like that. Implementation with maybe a digital. What about pros and cons? Before I show you what I put, anyone have any ideas?
Haptic links.
Yes?
It said that they are of different kinds. I think the reason is that they are different applications.
Yeah, that's right. It's
So
not.
this means that their number increases if you want to cover more and more applications.
It's true. Currently, this technology is still not very mature. So at this point, they're not very generalized about how to create the force feedback. So they have to create for multiple applications. And yes.
Like for economics, if you use this to save costs on lighting, because for instance, when we work on aerodynamics, we usually make many physical type to see how it feels
Yes.
to roll the product,
Yeah.
etc. So I guess it will save a lot.
Yeah. That's one of the ways you can use these. So for the pros and cons, Mutahar said that it's not very generalized. Here are some that I put. So it provides intuitive interaction, directly measure performance, and create immediate feedback information for the user, which is quite useful for a number of applications. As I said before, for example, surgery simulation. And it also saves resources in some applications. For example, to design ergonomic products, you don't have to create physical prototypes. For cons, actually, currently it is computationally expensive to both render the solid models and then create multiple solid models that correspond to the real world and define each how they should interact with each other and with the person itself, and then generating that interaction to actual force. And currently, there's also the issue of the update rate. The update rate has to be, I think, more than 1K hertz for it to actually feel real. And anything else you want to add?
I also read that you have to replace your haptic link after some time because it is a friction-based mechanism. So after some time, the friction will be lost in all of the multiple actions.
Use
Yeah.
where?
Yeah.
For the first system, it's quite intrusive because you have to have a lot of patches
Yes.
all around you.
A lot of. So ideally, when this haptic technology is mature, maybe you just want a glove or a skin tight bodysuit, and they will generate the forces for you, right? And there's actually one product like that called the Tesla Touch, but I'm not sure how effective that is currently. So yeah. Anything else anyone want to add?
The first video uses the muscle simulation to mimic the.
Yeah.
So I was wondering, how does it add constraint? Like, how does it limit your movement? For example, if you're holding the cube, you can't squeeze it too much, right? So how does it stop your?
So they said they use electrical shock, but I'm not sure how constant electrical shock can generate constant force. Maybe you can, create some impulsive force, but yeah, I'm not too sure about that either. How can they generate a constant force using the electrical shock method? So the hardware way using haptic links is maybe much more preferred if you want to create a constant force feedback. So if no one else wants to add, I will proceed to the next topic. So the next one is about design automation, and this is one of the example products.
TriQuant is used by engineers, non-technical staff, distributors, customers alike to automate design software models on a device. Imagine your customers browsing your products online.
I think it's already maximum, Professor.
Producing unique manufacturing information in minutes. TriQuant is sold and supported by over 100 SolidWorks resellers
I cannot use this.
by hundreds of companies around the world, and our solutions are scalable. From entry-level design automation with TriQuant Express, all the way to the web as an online 3D configurator with TriQuant Pro. You can integrate your TriQuant output data to other company systems such as ERP, CRM, and SolidWorks EPDM. TriQuant is designed to be simple to use. First, there is the setup.
And this is the example.
This can be split into 3 steps. To start, enter the information you would like to control. This can be anything from SolidWorks information.
So this is you as the company that creates the product. You first define what parameters can be changed.
With TriQuant, your UI can have a beautiful form and flawless function. Finally, the user interface and the output data must be connected. You can do this using TriQuant rules. Our easy-to-use rule builder makes creating complex rules simple. Once you've set up your project, you can make it available internally to your sales team and engineers, or externally to your customers and distributors. They can run TriQuant, allowing them to create custom design. So let's take a brief look at TriQuant use. Here, we're using our online demo site, configuremyproduct.com. This site shows how TriQuant can be used within a standard website. Selections are made to configure the specification of our scissor lift. The user may click to preview the model in 3D. When this button is clicked, the information from the web is sent to SolidWorks, where the model is changed. This then saved as a web-friendly 3D file and sent back to the device. Once the user is happy with their quote, they can click Finish. At this point, TriQuant generates the models and creates the relevant manufacturing information. It will also create sales documents and write data to the relevant company systems. All of this functionality is possible with TriQuant Pro. Visit our website for more information.
So in summary, that is just an example of how we can automate certain steps during the design process, so that it can be much more time saving. So for this example, the DriveWorks will you as the company that creates the product will define several parameters of your product that the customer can then specify, and when the customer specified their design decisions, you don't have to create a design from scratch anymore. You can just use those design parameters set by the customers and automatically generate the model. And you can also automate the creation of the bill of materials and other documentations. So based on your experiences of using solid modeling or CAD systems, what are some other ways that of the steps that can be automated? And what are the advantages and disadvantages of using such an automative system?
It's similar to one of the previous systems which was shown by Alex, because here you can customize.
Yeah, here it seems like you're just using predefined.
Motorcycle, you can make new models by making one, like you showed for one, capturing the parameters of one and then updating.
Sorry, but that's.
I think it is more towards a template-based modeling approach.
Yeah, for this example, yeah.
Yeah, so in the template, we define some parameters which user can change, but there could be some other parameters which are in some link with those parameters. So
yeah, this is just maybe an example of just a way to use that to automate the process. And maybe I couldn't find the same example, but maybe, for example, you can automate the process of the how to say the shape that you want. Maybe, like, for example, you want a cabinet, but then the customer wants the cabinet to be maybe curved. Then you can just select the templates and then automatically design that one. It doesn't necessarily mean you use there is a predefined object or parameters, but then it can easily maybe be much more freely customizable.
actually, in template-based modeling, there are some relations that you define by yourself. Like if you want to make scales in the ladders in template-based modeling, so what you will do, you will specify the height and number of steps, but the thickness of the poles and the ladder steps are defined based on the height and number of steps. So there must be some working inside the system.
Yeah, it still cannot be fully automatic.
How can this be different from a system that is customized to make different versions of the same?
Well, maybe they're not so different, but my point is that this is just one way of how a part of the design process can be automated.
I think their focus is assembly automation, right?
Yeah, but I'd like you to not focus too much on this example, as this is just one example, but I want you to think of maybe other ways, other steps during the design process or during your when you use SolidWorks that can be automated. And this is just one example. Or maybe at least the advantages and disadvantages if you want to automate some steps. Well, one way is repetitive tasks that you need that you have to do for when you create when you're during the design process, or when you're creating the final documentation. Maybe you don't have to manually put it in anymore if you just have the defined parameters in the model. So here are the pros and cons that are written. The automation obviously saves time, and it has the possibility to create a personalized design, but this is mainly for that previous example. Then you can also, based on their website, they can also integrate it with other systems. However, like with automation, there is less variety and less customizability, and then there's also the less versatile design. Anybody else want to add? Like, so maybe ideally in the real world, when you want to design something, you just show the computer a picture of what you want, and then they automatically design everything for you. But what are some disadvantages or advantages in this process? System yes. System dependence. Anyone else? Oh, if there's nobody else to add, nothing else to add, I will. That's all for my discussions. Here are my references. Thank you for your participation.
All right.